Alright, welcome to another exciting, awesome physics challenge where I challenge you to do physics and you're awesome. Things like that. Okay, so here's our challenge problem. It says Melanie is being nice to a younger brother. That is so rare, but it does happen. Younger brother Tyler by giving him a 3-second head start during a race. Melanie can run at 8 meters per second. Tyler can run at 6 meters per second. Assuming they can both start running from the same position, what position will Tyler be at when Melanie catches up to him? Oh, maybe they're playing tag or something. I don't know. So here's where you're going to actually, work your magic. You're going to see what you came up with and stuff like that. So make sure you pause the video right now, and then I'm going to show you how I solved it. Okay? So pause the video, come back. Seriously, pause the video. Alright, so we're back. Very exciting. If you did this correctly, remember to say, if I did this correctly, I hope I got it right, then you should have had a displacement. Sorry, I meant to say a position. So she would catch him at a position of 72 meters. Alright, that's where she would catch him. So if you got that right, fantastic. If you didn't, let me show you two. That's right, not one, but two different ways that you could solve this. So first of all, you could solve it by drawing a beautiful position time graph. So that's what I'm going to do, sketch out a beautiful position time graph, position and time. And then I've got Tyler going like this. There's Tyler man. And then I have Melanie. Now Melanie starts at a different time. She actually starts from here. But she's faster, so she has a steeper slope. So, this is my position time graph. Now, since I'm going to be using a position time graph, I'm going to be using my equation of final position is equal to velocity, change in time, plus initial position. So here's how I like to treat this. I like to actually shift things over, because if I was to solve for Melanie's, let's put an M there, Melanie's initial position, I'd have to actually go back in time, because I'd have to be like way down here. So she'd have to go somewhere back here, back in time, so that would be kind of weird. So, or she'd have to have a negative starting position at the least. So what I like to do is I like to just kind of shift this over. Alright, so I'm going to go to a different color here. What color makes me happy? Let's go light blue. I obviously shift over this right here, and I say, well, we'll shift things over. What is this? What is Tyler's starting position? So basically, I'm saying, let's make Melanie start at time 0, and then where would Tyler be? Well, that's pretty simple. I could do that, because if Tyler's going in average velocity, I'll use that equation. Well, how far has he gone in that amount of time? Well, Tyler's going at a velocity of 6 meters per second. So he's gone how far in 3-second head start? So I know that he starts at an initial position of 18 meters. He started from 0, so he's at 18 meters. So this right here is 18 meters. So now when I look at this graph here, I can go back to all the things we've always done in class all the time. Let's change colors, go back to black. So now I can say, well, here's the equation for Melanie. Melanie is using, again, we're using this equation right here. So we don't know the final position, but her velocity is 8. And we're looking for the time interval, plus her initial position is 0. Then we can go with Tyler. So Tyler, don't put equal sign, put dots. Tyler has a unknown final position. His velocity is 6. His change in time is also unknown, but we now know that his starting position in this scenario would be 18 meters. So that's two equations, two unknowns. So now we can do the old thing where, hey, let's just set them equal to each other and do some algebra. So I basically have 8t equals 6t plus 18. Algebra, you get the time of 9 seconds. So she will catch him in 9 seconds. But I want to know position. So all I have to do is punch that 9 seconds into either one of these equations. And if you punch into either equation, do some algebra, you will then discover that the position, the final position, is equal to 72 meters, and that is my answer. Okay? So that's one way you can solve it. But, as we've talked about all this time, we can always solve things in multiple ways. So let's look at it a different way. And that would be by using, anyone? Yes! You got it right, the velocity time graph. So, I'm going to draw a beautiful velocity time graph here. So, stick with me. I've got a beautiful velocity time graph. Velocity and time. So then I've got, we'll color code this a bit better. So let's go with red. So here's my boy Tyler. Literally, he is my boy. So that's Tyler. He's going along at a speed of 6. So that's Tyler. And then Melanie, she's my girl. Literally, she is my daughter. She's going at a speed of 8. No, this is not to scale. And oh my gosh, I drew that wrong. Why did I draw that wrong? Well, because she did not start at a time of 0. She started here at the 3-second mark. Okay? So I'm going to mark that so there's no confusion. This is the 3-second mark. So I could also use the velocity time graph to solve my problems. And I do that by looking at areas, because areas tell displacements. So this first area right here, this is how far Tyler has gone before Melanie even started. Well, that's 6 times 3, so that is 18. So that's his head start. Then, oh no, I hope you didn't see that. My PC's running out of power, so I'm running fast as I can. Then this is the area here. That's the difference in their speeds. So this is basically how much area Melanie has to make up. Well, what's that displacement? I don't know. But I can solve for that. Okay? And if she's going to catch him, this area here is going to be equal to the head start he was given. So I'm going to set up those sets of equations. So I basically say, well, delta x of the head start is equal to delta x of me catching up. So that's the 18 meters is equal to, well, how do I calculate this? Well, the velocity, or the difference in velocity, is going to be 2. That's my height. And then my base is this unknown time, which I'm actually just going to call it delta t, and that's going to represent this entire region right here. So I'll just call that a delta t. So I'll say, well, man, how much time passed? Well, that means that Melanie has to run for 9 seconds. So that's that. And then as soon as I say, man, she had to run for 9 seconds, well, then all I have to do is punch it back into the equation to figure out how far she went, or, her or Tyler. So I can say, well, this is 9 seconds, so I can say, Melanie, how far did you run in 9 seconds? Well, 9 times 8, because displacement is equal to velocity times change in time. So Melanie's velocity is 8, change in time is 9, so we get 72 meters. That's how far she ran. Or we could say, hey, Tyler, how far did you run? Well, we would not use the 9 seconds. We would do 9 plus 3, because this is 9, so that means this point right here ended up being 12. So we'd say, wow, what's 6 times 12? So delta x equals velocity times change in time for Tyler. So his velocity was 6. The time for him was 12. See that 3-second head start still equals 72 meters. All right? So that's how I know my answer is 72 meters. So hopefully you got the right answer. Hopefully you chose one of these two paths, and hopefully that made a lot of sense. All right? If not, come to class, ask some questions, and I will see you then.